I imagine that right now you're feeling a bit like Alice, tumbling down the rabbit hole. I can see it in your eyes. You have the look of a man who accepts what he sees because he's expecting to wake up. Let me tell you why you're here. You're here because you know something. What you know you can't explain, but you feel it. You felt it your entire life. You don't know what it is, but it's there like a splinter in your mind, driving you mad. It is this feeling that has brought you to me. Do you know what I'm talking about? Do you want to know what it is? You take the blue pill and the story ends. You wake in your bed and believe whatever you want to believe. You take the red pill and you stay in Wonderland, and I show you how deep the rabbit hole goes. So make your choice. Which will it be? Too slow, I picked for you. We're doing the red pill. Hi, friends. Let's continue our discussion of solving systems of equations, this time by graphing. Class 5.2, solving systems by graphing. So remember, last time we were together, we defined a system of equations as a set of two or more equations containing the same variables. If I'm working with the system, right, they all have similar notations to indicate that I'm thinking of a pair or a set of equations. I use this kind of set indicator symbol, my squiggly bracket, like I used for set builder notation. For example, maybe the system that I'm working with is this guy. Y equals negative x plus 5, and y equals 2x minus 1. It could be any equations, right? But as long as they have the same sets of variables, we know that we can think of them as a pair. Remind me, what am I trying to do by solving this system? My goal is to solve it. What does that mean? 5, 4, 3, 2, 1. Very good, Neo. Look at you go. So, to solve a system of equations, again, the idea of solving is to make it true. And if I want to make the system true, I need to make all of its parts true, which means to solve a system of equations, I'm trying to make all of the equations in the system true. So, for example, say that I want to determine whether or not 2, 3 is a solution of the system above. Take 30 seconds, take a minute, pause the video. How could you show me that this either does or does not make all of the equations in my system true? Go ahead. And stop. Look at you, Neo, doing your back bends, dodging your bullets. So if I'm dealing with this guy 2, 3, it's an ordered pair, which tells me x is going to come first, y is going to come second. If I want to show that this is a solution of the system, all I need to do is plug in and check that it does in fact give me 2 true statements. So, using my value of 3 for y, for the first equation, 3 would be equal to negative 2 plus 5, slotting my 3 in for y and my 2 in for x. Well, negative 2 plus 5 is equal to 3, so this does indeed make the first equation true. For the second one, I would say 3 is equal to 2 times x, which is 2, minus 1. 2 times 2 is equal to 4. 4 minus 1 is indeed equal to 3, so yes, this makes both of the equations in my system true. It is a solution. Cool. Now that's all well and good, but it's not good enough for mathematicians. Again, we took the red pill. So we want to know, now that I have a system of equations and I have a solution to the system of equations, what does the solution tell me about the system? So think strategically here, think creatively. I'm telling you that the ordered pair 2, 3 makes both of these equations true. What do you think that tells you about those equations? The hint that I'll give you is look at the form that I've written those equations in. What do you think that 2, 3 is in the context of this problem? Take 30 seconds, take a risk, take a chance, make a guess. Go ahead. Okay. Hopefully you've noticed, right, what I'm really doing by talking about a solution of a system. We'll notice that the solution 2, 3, that's an ordered pair. Another word for an ordered pair that we've seen, we can also call an ordered pair a point. And if you look back at both of those equations, notice they're both in y equals mx plus b slope-intercept form. Those are lines. Now 2, 3 is a point that makes both of those equations true, which means that 2, 3 is a point on both of those lines. And if I have a point that lives on both lines at the same time, what that hopefully means for you is that this point needs to be, for the most part, the points on the lines will be different, but if I find a place where they have the same point, that must be where the lines intersect. So, what we are really doing by finding a system's solution is finding the place on the graph where the two lines cross each other, where they meet. Which means, if we can graph our lines, we should be able to use the visual of the graph to find the solution, because the solution should be the place where they cross. Which leads us to our first method for solving equations, or systems of equations, solving by graphing. Say that I take that same system from above, y equals negative x plus 5, y equals 2x minus 1. I already know what its solution is. It's 2, 3. Graph these lines. Remember, how do I graph in slope-intercept form? Put these two on the graph. Can you show me that they intersect at the point 2, 3? Go ahead, take 2 minutes, pause the video, see how far you get. Do you remember how to graph in slope-intercept form? Have fun. Okay, cool. Hopefully you got there. So, y equals negative x plus 5. It's already in slope-intercept form, right? I have an m and a b. I have an m and a b. So for my first line, that tells me its slope, it's the coefficient of x when y is by itself. So negative 1 over 1, or just negative 1. I like to write it as a fraction because I want to use my rise and run to find points. And then my y-intercept is 5. Same thing for my second line, right? Its slope is 2, and its y-intercept is negative 1. Starting with our first line, I'll do it in green. So this guy has a slope of negative 1 over 1. Its y-intercept is 5. So its y-intercept is 5 on the y-axis. 1, 2, 3, 4, 5 is right here. So that point would be 0, 5. Using my slope of negative 1 over 1, so I have a negatively sloped line, so I need to go down 1 and over to the right 1 if I want a decreasing line, so that tells me there should be another point right over here. This guy has the coordinate 1, 4, and if I find one more point on my line, down 1 to the right 1, that point is 2, 3. Which should be unsurprising for us because we showed that 2, 3 lived on our line up above. Y equals 2x minus 1. I'll do this guy in blue. Its slope is 2, its y-intercept is negative 1. Let me start by putting that y-intercept down over here. So if the y-intercept is 1, again, x is 0, so 0, negative 1 is my point. For my slope, right, if I think of 2 as 2 over 1, so I have a positively sloped line. Every time that I go up 2, I need to go over to the right 1 to find another point. So this guy here is 1, 1. Same idea. If I go up another 2 and over 1, it would get me to this point, which unsurprisingly is 2, 3. That's the same point that we found above. So here's our blue line, our second one. Here's our green line, our first one. Fantastic. We can now see visually that this point, 2, 3, is a shared point between these equations. So indeed, what I'm doing by solving the system is finding their point of intersection. Good. So here is my solution, 2, 3. Magnificent. Let's try another. Same idea. Take these two equations, y equals 1/2 x plus 3, and y equals negative 3 halves x minus 5. So we want to graph these two equations. We want to find the point on the graph where they intersect. And then just to make sure that we've got it correct, we'll check our work after to make sure that that point is indeed the solution of our system. Take 2 minutes, pause the video, see how far you get. Go ahead. Okay, y is equal to 1/2 x plus 3. So if I take this line, I'll do it in green as I did above. Its slope is 1/2. It's a positive slope, so it's going to be an increasing line. Y-intercept is 3, right? I'm in my y equals mx plus b form. Might as well use it. So my y-intercept, 1, 2, 3, is right over here. The point 0, 3 is on my graph. From here, I want to find some points on my line. So I'm going to use my slope of positive 1/2. If I go up 1 and over 2, I'll have a point over here. This guy's coordinate would be 2, 4. Maybe for variety's sake, I want to go the other direction. So if I go 1 down and 2 to the left, I should have another point on this line. This guy here would be at negative 2, 2. I'll draw in my line here. We're going to pretend that it's a beautiful straight line that connects our points. Fantastic. Y equals negative 3 halves x minus 5. So here, this guy has a slope of negative 3/2 and a y-intercept of negative 5. So I'm going to start by putting down my negative 5. 1, 2, 3, 4. Negative 5 is right over here. So there's 0, negative 5. Slope. So I'm going to go up 1, 2, 3 and over 1, 2. So there's a point over here. This guy's coordinate is negative 2, negative 2. And then if I go up another 3 and over another 2, would you look at that? It looks like that point here, which would be at negative 4, 1, should also be on the graph of my green line. Nice. Let's show that this guy, negative 4, 1, it seems to be the point of intersection. Let's quickly check and make sure. So I want to check that negative 4, 1 is my solution. In order to do that, all I need to do is substitute. So let's take y is equal to 1 and x is equal to negative 4 and do some substitution. In our first equation, I know that 1 should be equal to 1/2 of negative 4 plus 3. Here, half of negative 4 is negative 2. Negative 2 plus 3 is indeed equal to positive 1. This makes our first equation true. And for our second one, 1 should be equal to negative 3/2 of negative 4 minus 5. So from here, I need to do negative 3/2 times negative 4. That's not too bad. Negative 3/2 times negative 4/1. If I cancel out here my common factors, well, I've got a 1 and a 2 left over. Negative 3/1 times negative 2/1 is positive 6. 6 minus 5 is indeed equal to 1. This ordered pair makes both of my equations true. So I can say that negative 4, 1 is indeed the solution to my system. Magnificent. One more for the road. What if I'm not in y equals mx plus b form? Well, I'm giving you a hint. Maybe you might want to get there. If you want to, you can use a table. That's totally fine. When I solve this guy, I'm going to convert both of them to y equals mx plus b, but it is absolutely up to you, whichever you prefer. Either way, let's graph these two equations, find their point of intersection, and make sure that it is indeed our solution. Go! Alrighty, so I'm going to take each of these equations. Let me start with the first one here. So I've got 3x minus 4y equals 12. I want to get it into y equals mx plus b form. So I'm going to start by subtracting 3x from both sides. So I'm going to rewrite this as negative 3x plus 12 on the right side after I subtracted 3x from both sides. All I need to do now is divide both sides by negative 4 in order to get y by itself. So that tells me that y should be equal to 3/4 x, right? Negative 3 over negative 4. Negative over a negative is a positive, minus 3. So here's my first equation. And for my second equation, I know 2x plus 4y is equal to 8, minus 2x from both sides. So I've got 4y is equal to negative 2x plus 8. Again, we're going to divide both sides by 4 here instead of negative 4. So I've got y is equal to negative 1/2 x. 2 divided by 4 reduces to 1 divided by 2 plus 2. Cool. Taking my equations and graphing them. So I'll say this guy is my green line on top. This guy is my blue line on the bottom. So it has a slope of 3/4 and a y-intercept of negative 3. So I'll start by putting that negative 3 on my graph. So here's 0, comma, negative 3. From here, I'm going to use my slope. So if I go up 1, 2, 3, and over 1, 2, 3, 4, this point should be on my graph at 4, comma, 0. If I wanted to go in the other direction, right, I could go 1, 2, 3, down, and 1, 2, 3, 4, over. So I've got another point over here. This guy should be at negative 4, comma, negative 6. Let's connect our points with a line. There we go. We're pretending that this line is perfect and straight and connects all 3 of our points beautifully. There's our graph. For our second one, right, its y-intercept is 2. So I'll start by putting 0, comma 2 on my graph right over here. And I know that negative 1/2 is my slope. I'm going to be strategic here. I'm going to find points only to the right. You'll see why in a second. So I'm going to use my negative 1/2. So if I go down 1 and over to the right 2, I'll find another point over here. This guy's coordinate would be at 2, comma 1. And then if I use my slope again to continue going to the right, look at that. I've got another point right here at 4, comma 0. So it looks like 4, comma 0 is going to be our solution. Let's check. So I want to check if 4, comma 0 is indeed the solution to my system. Well, I know I can use either equation, by the way. Let's say that I used these equations. So I want to see, is 3x minus 4y equal to 12 when 4, comma 0 is my possible solution? So from here, I'm going to say 3 times 4 minus 4 times 0 equals 12. 4 times 0 is 0, so I can ignore this guy. 3 times 4 is 12. 12 is equal to 12, so it makes our first equation true. And for our second one, I've got 2x plus 4y equals 8. Let's substitute 2 times 4 plus 4 times 0. Is this equal to 8? Well, again, 4 times 0 is 0. 2 times 4 is 8. 8 is equal to 8. Would you look at that? We found our solution.